Hello, and welcome to the 7th online lecture in the GlobeDrought series talking about how to characterize drought. My name is Natalie Cornish, and I am one of the main project leads working on GlobeDrought at a company called Remote Sensing Solutions, GmbH. As a commercial and research institute specialized in remote sensing applications, it is our goal in this project to advise and support drought-related products derived from remote sensing.
Welcome from my side. I'm Gohar Ghazaryan, Research Associate at Center for Remote Sensing of Land Surfaces of University of Bonn. Within the GlobeDrought project, we contribute to derivation of different remote sensing indicators at regional to global scales for monitoring of drought impacts and vegetation condition.
Our three main objectives for this lecture are first, to introduce how remote sensing supports and fits into the framework of GlobeDrought. Second, introduce common satellite systems and indices used in vegetation health monitoring. And three, give concrete examples of how vegetation health and drought impact can be detected at a regional and global scale using remote sensing technology. In the previous lectures, we introduced the concepts of drought hazard, vulnerability, exposure, risk, and impact. Almost all of these components can be quantitatively assessed using remote sensing. Just last lecture, Helena Gerdner explained that the GRACE mission, for example, contributes to hazard. This is just one example and one satellite system that can be used in this context. Other examples include precipitation, groundwater, detecting crop yield and irrigation patterns, or even changes in climate. For this lecture, we're going to focus on vegetation health and how we can detect that using satellites. For those of you who couldn't watch the previous lectures, the definition for remote sensing is observing and gaining information about Earth without actually coming into physical contact with it. The underlying physical phenomenon that makes this possible is that different materials respond differently to electromagnetic radiation. Many satellites nowadays record in the visible, near-infrared, and short-wave infrared, which translate indirectly or directly to physical properties in vegetation. These unique signals make vegetation and their condition readily distinguishable from space. In addition, satellites detect over large areas at very high detail and at a relatively low cost. In addition, the satellites have been available since as far back as the 70s, making it a very valuable tool for environmental monitoring on both large and small scales. Multiple satellites are used for vegetation monitoring today. Some examples include AVHRR, MODIS, Landsat 8, and Sentinel-2. Although they are used for similar applications, they do differ in their technical specifications. For example, some satellites image more frequently than others, which is their temporal resolution. Others collect more detail, which is the spatial resolution. And yet others see certain wavelengths of the electromagnetic spectrum that others cannot, which is their spectral resolution. What all of these examples that I just listed of satellites have in common is that they see in the red and the near-infrared bands. This brings me to one of the most commonly used vegetation indices called the Normalized Difference Vegetation Index. This uses light in the near-infrared and red and differences the two and then calculates it against the sum of the two signals in order to have a value between -1 and 1. The higher the value, or more positive, the more likely that the object you're looking at on the ground is green, healthy vegetation. The more negative or lower the number becomes, the more likely that it's not. As such, you can detect whether vegetation is under stress or in a healthy condition, purely from a simple index. If we look at a time series of NDVI, you can even detect global phenomenon, such as the changing of the seasons. So when plants start to become green in the green upslope, and when they senesce in the brown downslope. Just because NDVI is one of the most well-known indices in vegetation health monitoring, it doesn't mean that it's the best for every application. Some more advanced indices take given measurements and look at them versus the long-term conditions in order to say something about whether it's a normal or irregular state. Some examples of these indices include VCI or TCI, which look at NDVI and brightness temperature in contrast to a time series. And they look at the study of the change of moisture and the thermal state of vegetation. If we take these two indices and we combine them together in a weighted combination, we come up with a vegetation health index, which tells us a more complete story about vegetation condition over time than the single indices alone. Today, extensive studies have shown that this particular index, VHI, can be categorized with different thresholds in order to indicate improving or diminishing levels of vegetation health.
Besides NDVI and different indices that can be derived from it, remote sensing provides other data that can describe vegetation properties and condition. Leaf area index is one of the key variables in vegetation growth analysis due to its influence on biomass production, plant growth, and ultimately on yield. It is defined as the total one-sided area of leaf tissue per unit ground surface area. Due to availability of remote sensing-based time series of leaf area index, other metrics describing phenology can be extracted, which depict stages of growth from sowing to harvest. The phenological dynamics in general reflects the response of vegetation to dynamics of climate and hydrologic regimes. When applied over large areas, variations of vegetation growth stages, such as shifts in the start of the season or declined maximum value, can be observed, which can further indicate the adverse impacts of unfavorable conditions for vegetation growth, such as droughts. One of the most significant components of hydrologic budget is evapotranspiration. It is the water loss to the atmosphere by two processes, evaporation and transpiration, and it can give an important information regarding vegetation condition. Remote sensing is considered one of the most important tools of deriving evapotranspiration over large areas. Specifically, metrics such as actual and potential evapotranspiration can be derived. Actual evapotranspiration indicates the flow of water from the surface to atmosphere, while potential evapotranspiration represents the atmospheric evaporative demand. Based on these values, we can derive metrics such as the ratio between actual and potential evapotranspiration, which can indicate the intensity of drought impact. Further, with the use of different remote sensing-based metrics such as spectral bands, normalized difference vegetation index, which were discussed earlier, and machine learning, we can estimate the crop yield with high spatial resolution and several months before the harvest. This information is valuable for different stakeholders such as farmers and decision makers. Finally, one of the advantages of remote sensing is the global coverage, so the outputs that we generate can be at the global scale. One example of this kind of output is the percentage of cropland area affected by drought at the country level. This is possible with the use of different time series coming from sensors such as MODIS and estimation of different vegetation indices such as vegetation condition index. But here we integrate also the land cover information, so the area that are impacted by drought can be delineated. Some concluding remarks from our side. So we've seen that remote sensing derived metrics can be used effectively to characterize vegetation growth stage and condition. Nevertheless, we have to remember that in situ data is still necessary to verify remote sensing-based vegetation condition information. Still, the synergistic use of multi-source remotely sensed time series gives information on varying vegetation condition from global to local scales.
Before we go, we'd like to thank you for watching this lecture, and we'd like to remind you that the forum discussion is now open for your comments, feedback, and questions. In addition, there will be a longer webinar on exactly this topic, so global drought and remote sensing, that you can watch soon. And if you're following the full series of GlobeDrought lectures, the next one will be on vulnerability and the risk of sectoral drought impacts.